Okay. So that's the Hermite form. This is the Hermite form, and I'll abbreviate that as H and F as Hermite normal. Okay. Questions about how I'm writing or the size? The size okay for the writing? Good enough? Okay, good. Okay, and if you have questions throughout, you just ask, interrupt me, and it's perfectly fine. Okay, especially if you can't understand what I'm writing. Okay, yeah, that's the Hermite normal form. That's great. I want to talk about one more normal form that we've seen before, I'm sure, but it wouldn't help to at least write some notation down. So by acting also on the right, by GL and Z, there exists a unique diagonal matrix. I'll use S. I used H for Hermite. S, GLN plus Q, which is diagonal. I'll put it up here this time. And it satisfies two properties, namely the entries, and of course I'll use the same style of notation. Capital S will be a lowercase sij for the entries there. We have that the diagonal entries have this divisibility property. Moreover, and importantly, S, GLN, Z, we get that equality. So if I look at the orbits of the left and the right, they'll be the same. Yes. Why do I have to? I don't have to for this. No, I don't have to for this, but throughout what I'm going to talk about. Actually, I'm going to talk about this very soon, in fact. I'm going to talk about lattices, and the what I mean by lattice will be essentially an integral matrix with non-zero determinant. Yeah, no, for this I don't actually need that. Cool. Other questions? No. Which definitions? These two? The motivation is to kind of give us a normal form. Actually, maybe it'll help with this example, and then I'll come back to that. Let's look at this example right here. Yeah. So let's look at n is 3. Okay. So M, an integral matrix with non-zero determinant, I claim is this one. And it's Hermite normal form. Okay. One of the motivations for these normal forms is that we can see some of the properties of this matrix. And it's Smith normal form. I'll put it down here. 1 to 40. Okay. So, I mean, of the many properties we could observe from these two normal forms, we can very easily see either from this matrix or from this matrix that the determinant is 80. But we can see a bit more of the properties if we're looking at this. If I think about this as a lattice, and I'll explain what I mean, we can start to see the type or the cotype of that particular lattice. Okay, so this is an example of an M, an H, and an S. Okay, let me relate this to lattices, and then that might help with also this motivation here. Okay, so what does this have to do with lattices? I'm sorry? Sage told me it was. I don't know. I literally just got this from Sage. So subtract this one from that one. Okay, so you get 0, a 3, and a 7. And 3 times the third row. Yeah, I'm not able to follow that, but yeah, I guess they could technically be incorrect. I thought I grabbed an example from Sage and it was correct, but perhaps I have a typo somewhere. Perhaps I have a typo somewhere. So, I don't know, as an exercise, figure out the right M. No, I'm kidding. Yeah, I don't know. I use Sage to grab some of this, and unfortunately, I seem to have made an error. But I'm pretty sure these two would be correct. If I had this one or Hermite form, I would get that Smith.
This H must satisfy those conditions. Dual is equal to H ideal distance.
Yes.
So the second row.
What's not true in the second row? This is just some random matrix M. This is an integral matrix M. This is the Hermite form. Yeah. So I've got some diagonal entries here. It's upper triangular, and the entries above are less than the ones in that column. Yeah. And here I got the divisibility conditions. 1 divides 2 divides 40. So you think, you're saying that it's probably correct, actually, this M. Okay.
I think S is definitely correct, because
we can move on, and you can put this into Sage. It's only 9 numbers. All right. How does this have to do with lattices? What does this have to do with lattices, right? So for us, I should say for me in this lecture, I'll keep it singular, a Z lattice of an n-dimensional Q vector space V is a free Z module, lambda, let's say, inside of V, of rank n. Okay, in particular, we'll have finite index if I take the quotient inside of Z to the n, for example. Okay, what we're going to be doing is we'll be concerned with sublattices of a fixed lattice. Let's just call it Z to the n. Okay, if you have your favorite lattice inside of some n-dimensional Q vector space V, you pick your favorite lattice. I'll just pick Z to the n because it's easy. Okay, so we're going to be looking at sublattices inside of Z to the n, okay, in particular. And why do I define these matrices, ones with non-zero determinant? Well, if I take the row span, if I take the Z span of the rows of M, I obtain a lattice. So the row span over Z of M yields a sublattice of Z to the n. Okay? Now, I'm actually going to be working primarily with matrices, but if you wanted to consider these as lattices, you just think of it this way. Okay? So each lattice, sublattice, I'll say, sublattice of Z to the n, determines a unique Hermite form. After some choices have been made, okay? Choose a basis, for example, okay? So each sublattice has associated with it a Hermite normal form, a matrix of this type with those properties, all right? Of course, that requires some sort of basis or something there, so I'm not writing that, okay? What else do I want to say? Oh, yes, right, and such, maybe I'll say, and matrices of, can I say matrices of Hermite form? Let me explain what that means. Matrices of Hermite form, I just mean any matrix, upper triangular, that satisfies those properties, namely that it satisfies this particular property right here. Okay, I don't have a capital M to talk about here. Any matrix of this form, and matrices of this Hermite form, determine a lattice, of course. Determine that same lattice. Determine that same lattice. In other words, you can go back and forth. You can go back and forth. Okay? So if I have a matrix M and a matrix H, these two matrices will generate the same lattice, right, by their row span. Of course, that may not be true with the Smith normal form, and in particular for this example, these two matrices would generate the same lattice. However, this would not. This would be a slightly different lattice. Okay? And the index of the sublattice in Z to the N is the determinant. When I'm thinking about it in terms of matrices. All right? Okay. Great. So actually, this was mentioned the first day, the first talk. Christopher mentioned this, in fact. Why do we have these forms? Well, I mean, okay, there's many reasons why one would care about the Hermite and the Smith form, but what we can do in the context of this conference is we can use these forms to count subgroups of Z to the N. And I think this was even written already, the subgroup zeta function. Okay, so the subgroup zeta function Z to the N of S is the sum of all sublattices of Z to the N. Okay, I'll write the F here. I'll do what Benjamin did. I'll put it in orange, and then I'll just drop it from now on. Right, so I care about finite index. And of course, if I'm saying the word lattice, I've already baked that into my definition. Nevertheless, we're going to record the index. Okay, so that's the subgroup zeta function of Z to the N. Okay, and by the structure theory of modules over PIDs, or even simpler, Chinese remainder theorem, we get the Euler decomposition, right? So I'll just say, by structure theorem, we get Euler decomposition. All right, and I believe Christopher mentioned this on Monday. You get a product over all the primes of these local factors. Okay, and I'll just jump straight to it. We can look at ZP to the N. So these are the p-adics here for me. Okay. So it's actually a bit more convenient, and what I will be doing is I'll be working primarily in the local case. So for me, more convenient to be local. So I'm going to be primarily talking about ZP lattices, or in particular ZP matrices, and it will be essentially the same sort of thing. So instead of looking at, in particular, this GN plus Q, I'll be looking at GN plus QP, which would be exactly the same, except you've got a QP here and you have a ZP here. Okay. All right. So I'm going to be primarily talking about now p-adic lattices in order to try to, understand these integral matrices. Okay. A note. This works more generally. What do I mean? I mean, you don't have to work with just the p-adics and QP. You can look at extensions of these. You can take some number field, look at a ring of integers, complete it at a non-zero prime ideal, and you can work over those, okay? So you can work over any compact discrete valuation ring, and this will be just fine. It need not be characteristic 0, it could be arbitrary characteristic. Okay? If that makes sense to you, you're allowed to just, switch out every ZP with your favorite compact discrete valuation ring. Otherwise, I'm just gonna keep writing ZP. All right? Let's try this one. All right, so, right, the normal forms, the ones I've just erased are still carry over to talking about ZP. All right, let's look at an example real quick. We'll do my favorite prime, p equals 2. For those that know me, that's a joke. They'll have caught that. This is my most dreaded prime, perhaps. So this has nothing to do with this example. I don't mean to claim that this is this example here, p-adically or whatever that might mean. Okay, so it's just a different example. Trying to write it in a particular way. Okay, so we have some p-adic matrix, and just for emphasis, this is mat 3z2. Okay. That Hermite form Sage claims is this. Okay. And then the Smith is, I'll write it like this, 2 to the 0, 2 to the 1, and 2 to the 4. Okay. So in particular, it has a determinant 32. Okay, 2 to the 5. And we can still, well, yeah, it can get a bit tricky talking about less thans and ordering. You can come up with something in terms of valuations. I'm not going to get too into it, but in this particular case, you can think of these as kind of like as integers, and you can talk about that. But I don't want to get into that, and what I'm actually going to do is I'm not going to care too much about the Hermite normal form in its entirety. I'm going to care mostly about these numbers, and that'll be all right. That'll be all right. Okay. But it's something to hold on to. Okay. Some notes. For Hermite over here, you'll note that the diagonal is all powers of 2. You can always do this, powers of p. P on, I'll just write diag. Okay? We always have powers of p on the diagonal. Okay? We can always do that. We can always scale away the units there, and we always get that. For Smith, we always have a partition, maybe a backwards partition. Okay? The exponents give us a partition. Exponents yield a partition. Okay, and just maybe a reminder, let's see how much time I have, good. A reminder here, partitions, this is from Amritanshu, right? So we've got a lambda, be written as perhaps lambda 1 through lambda n, okay? And we have such that lambda 1 is greater than or equal to all the way down to lambda n. Okay, so the largest one is the first one, the smallest one is the second. Here, of course, the lambda i's are non-zero integers. Non-negative integers. And yeah, I'll just leave it at that. I don't think we need much more. I'm not going to go into more notation on partitions. Okay, so the Smith form determines a partition from the exponents. The Hermite form, not quite a partition. In this particular case, it's a bit ordered, but not quite a partition in general. Okay, where are we? Here we are. So, one can use the Hermite normal form to count subgroups to answer this question, to determine that zeta function over there. Namely, we have Z p to the n of S is what? Well, you could sum it over all of the matrices. All right, this is H in Gn plus Qp, where H, I'll just write Hermite. Okay? There I'm talking about a particular form. I'm not going to do this computation. I'm just going to mention that you could if one wanted to. I'll actually tell you that someone has, or people have, in particular, of color. Yeah, here we are. If you want to see how this could be done, you could look up the reference. Bushnell, Reiner in 1980. Okay, so they computed the subgroup zeta function for Zp to the n using basically counting by Hermite normal forms. Did more things as well. Okay, so another way we can count is not by Hermite, but rather by Smith. Instead, well, you're going to use the Smith normal form. And we're actually going to do this one. Well, most of it, not all of it. Okay. Oh yeah, I do want a little bit more notation. If I'm going to go back to the partitions here. For me, partitions, these are allowed to be 0, as I've mentioned right here. I'll write lambda is in p to the n, p sub n, sorry, to indicate that it has at most n parts here, has at most n parts. Now I'm realizing that parts is a technical term here. Part is any lambda sub I that is non-zero. Lambda I non-zero. So a part is any one of these terms that is non-zero. Okay, that's what I mean by a part, and that is a technical term. Okay, so partitions, my notation for partitions with at most n parts is given by that. All right, we're going to use the Smith normal form, so let's do it. All right, so suppose I want to define something here. Lambda is a partition with at most n parts. Okay, and I want to find this function, f sub n of lambda zp. Okay, this is going to count the cardinality of a set. This is the cardinality of all lattices. So that is zp to the n, such that the Smith normal form of the lattice of lambda is given by, I'll explain this, lambda. Okay. What do I mean by given by? I'm going to look at this example and explain by example. Okay. So lambda gives me a partition. The largest part is up here at the front. The smallest is lambda n. So what I mean by given by is I mean the Smith normal form. The exponents will always be p to the something. The exponents are given by the partition in reverse. Lambda n, n minus 1, all the way down to lambda 1. Okay? This condition ensures the divisibility condition of the Smith form. Okay? So that's what I mean by given by lambda there. Okay, let's get off. So we have this zp to the n. And what can we do? Well, we can count all these sublattices by Smith normal form. Let's do that. Let's determine a partition, lambda in Pn. Okay, we're going to sum over all the lambdas and Pn's, and we want to count all the lattices with this particular Smith normal form. Right? By running through all the partitions, we can ensure that we've covered all lattices. Okay? So what is this? This is just Fn comma lambda zp, right? That count of this set times, well, the determinant of the matrix that we would get from this Smith normal form. Yeah, question?
I have a question. So you're using Hermite normal form for, let's say, p-adic integers, but there is no order. So your condition of ordering the
I don't actually need it to be, I don't need to actually ensure anything up here. All I really need is this diagonal when I'm talking about p-adic. Sorry.
Doesn't it come from the division algorithm? So whatever your remainder you can get after the division, which means that the valuation is smaller.
Yeah, you could put some valuation conditions. I don't really.
Is it false that the Hermite normal form can be defined by just saying that the valuation of each entry in the column is less than the valuation?
Well, then you can. I mean, you could always take. I could add this row to this, for example, and the valuation would stay the same, but it would be a slightly different number. You can think about it in Z, yeah, and have the same condition if you like. I don't particularly care about this strictly upper triangular part when I'm talking about normal forms, in particular the Hermite, I mean. I really particularly care about these diagonals, and that is always the case.
You need a unique matrix, so then of course you have to care.
What do I need a unique matrix for? Perhaps for this I would, but I'm going to leave it to them to solve those issues. I don't in particular. Indeed, yeah. That's exactly how you can think about it. Yeah. There's a unique representative. Now if I look at the finite quotient by this particular element in Z2, all right, I could write them unique to that if you'd like. Okay. I just don't really care about that upper triangular part. Where was I? Yes, okay. So I need the determinant. That determinant is p to the lambda 1, lambda n, s. Okay? So I have that p to the s, minus s, sorry, coming from the index. We know the index is the determinant, and that determinant is the sum, p to the sum of all the lambda i's. All right? I don't like this particular relation when I'm dealing with this. It's a bit harder to count, so for me, it'll be a bit easier to look at alphas in a vector of non-negative integers, alpha. I'm going to write this and I'll explain it. So what I have from an alpha, any sort of vector like this, I can determine a partition, call this alpha here. I can determine a partition, lambda alpha, by adding from the right. I would have an alpha n here. I would have an alpha n minus 1 plus alpha n, and so on and so forth until the very first coordinate would be alpha 1 plus all the way up to alpha n. Okay? This would define a partition. And that is indeed what I'm going to do. I'm basically just taking their differences, this would be, you could view this as a partition, lambda 1 minus lambda 2, for example. Okay? So instead of working with partitions, I'm going to work with a composition and then kind of generate a partition from that, a unique one. And this just changes the numbers just slightly, but not in a very complicated way. All right? So I've got something like that. The determinant now is given by this, and you can double check that the sum of the lambda i's is indeed this weighted sum of the alpha i's. Okay, now we're ready to go, except that we need to know what this number is. And we can turn to a classical theorem of Birkhoff from 1935. Or if you want a modern version of this, you can go to Butler, and this is 94. Okay, and that says Fn lambda alpha Zp is given as follows. Product given by this. Oh, and maybe I'll say what the j is. The j of lambda alpha, I'll just write this in terms of alpha, j coming from the jumps of this partition, but it's going to be all the i's in 1 to n, where alpha I is not 0. The alpha i's kind of record when this thing jumps. So you get something like that. Okay? So this is actually a specialization of Birkhoff's formula. Birkhoff's theorem and the theorem presented in Butler is a more general version of this, counting subgroups of a specific type inside of a finite abelian P group. Okay, and this gives us exactly what we need. So I think Christopher also mentioned this function. I'll mention this. This is the Agusa function. In y. I'm going to use z1 for variables, zn, not to confuse some other things later on. And then we're going to run through all the subsets of n, take that multinomial coefficient relative to y, and then we've got a whole bunch of geometric progressions determined by the set I. There's our Agusa function there. And this is going to help us record and determine this zeta function here. All right? So that's the Agusa function, very useful, has a lot of applications in terms of lattice counting. I won't list all the references, but it comes out quite a bit. And I imagine it might come up in Angela's talk in her mini course. Maybe, maybe not. Certainly, Angela has quite a background with Agusa functions. Likewise, Christopher does as well. Anyways, this is a pretty useful function. It's not just used here. Good. So the proposition then, we've got this subgroup zeta function. Is a substitution of this Agusa function right here. Okay? And that substitution is, for the y, I'm going to put in p to the minus 1. Okay? You can see this coming in from that Birkhoff formula right here. Okay? And then the rest, I'll lump them all together. Make sure I get everything correct here. So for the variables zi, I'm going to replace zi with p to the I times n minus I times s. Okay? And I want you to pay attention to this. I'm going to draw an analogy, not today, unfortunately, but tomorrow, to this. This right here, okay, it's a number. It's I times n minus I. But you could think of this as a dimension of the Grassmannian. In particular, the Grassmannian that records the I-dimensional subspaces in an n-dimensional vector space. Okay? I only mention this now. I won't be able to reference it later. In particular, I won't have it on the board, of course, in my next talk. But remember this. This is going to be sort of generalized, and there's going to be an analogy that I'm going to play off. Okay? And of course, this is, as probably Christopher mentioned, this beautiful formula. Okay, that's that local zeta function there. Okay. Explain this notation right here. Yeah, this is this multinomial coefficient. This is what's called the multinomial y, or the y multinomial coefficient, I guess. Yeah, so what is this thing? I'll mention it right here. So if I have nky, this is just two numbers, now not a set. This is nothing more than 1 minus y to the n, 1 minus y to the n minus 1, all the way down to 1 minus y n minus k plus 1. Okay, on the numerator, and on the denominator, you go up 1 minus y squared, all the way up to 1 minus y to the k. I think I've got it right. What's really quite nice about this is that this factorizes. It's not a rational function. It actually simplifies to a polynomial in y. Okay? So what is this? This is the product of the usual y binomial coefficient. And there's perhaps a million different ways that one could write this product down. Let's see if I can get it right. I would start off with n, and I would take the max. Here, let me help myself. Oops. All right, let's say that's an order. So this is the smallest element, and this is the largest element, I sub L. I think I would take this as I sub L first at Y, and then I would go from I sub L to I sub L minus 1, Y, all the way down to the last one, I sub 2 and I sub 1, Y. I think that's one way one can express this thing. Okay. This is a big polynomial in some sense. Good. Right. Okay. So that's Smith normal form. That's Hermite. And those are applied individually and separately. Let's track them both at the same time. Okay, let me give you a definition. Yeah, that's one way to interpret that, indeed, yeah. Yeah, that's perhaps one way you could write it. It doesn't need to be. You could count a subspace and then a subspace of that and a subspace of that. I think this is perhaps okay. You could rearrange. I'm not saying you couldn't formulate it to have n's in the numerators here.
Just thinking of picking a one-dimensional space first and then the three-dimensional space,
There's probably, okay, I could perhaps have a typo. I'm not entirely sure, but I think this is correct. You could have multiple interpretations of this counting problem. There's a lot of symmetry with these binomial coefficients. I believe it's correct, but that doesn't preclude that there's multiple ways to write this thing. Okay. Oh, here we are, over here. I wanted to find one bit of notation before I get to writing this. Lambda is still a partition then. Inc for increment, okay? Inc for increment, I want this to be the associated composition, if you like. Okay, now this is not a partition anymore, this is just some vector of non-negative integers. Okay? Inc, increment. What happens to what if you put y equals 1? Here, you're going to get the usual binomial coefficient.
Which is n factorial divided by?
N factorial divided by k factorial times n minus k factorial.
No, the next one. I mean, I'm just confused about what I stands for.
I is a set from 1 to n. A subset, I should say.
Okay. So I doesn't sum up.
No. You have that condition there. Yeah. Okay. So, definition. The Hermite-Smith series, the thing I want to talk about here, is as follows. Hs sub n, and I'm going to have a number of variables. I'll describe that in a second. Lowercase x, lowercase y. This is going to be that's an n and that's a p. Lattices in Zn to the p, Zp to the n. X inc y. Oh, and I didn't mention this. I'll mention what the delta x is, the delta lambda is. Delta lambda is as follows. Actually, I'll explain it on the other board. I'll just explain it on the other board. I don't want to squeeze it in there. So I'm erasing the example, but this is what I mean by I only care about the diagonal entries. Delta lambda. You can think about it. I'll explain it in a different way, but if you like, through matrices, you associate a Hermite form from lambda, and then you pick up the diagonal entries. it'll be something like p to the delta 1, p to the delta 2, all the way down to p to the delta n. I don't really care what's up here. And delta, lambda, is going to be the vector of these delta i's. Okay? Now, you don't even need a normal form. You could just take it into any upper triangular form where you've got p powers here. Let me write the 0 there. Okay? Doesn't matter what's up in the star, whether it's unique or not. I don't really care. Okay? That's the delta. And, right, and the lambda is, of course, the Smith type. And I guess I should perhaps say, what do I mean by this? A set of variables here, y2, I'll just use alpha as a placeholder for some n-dimensional vector. This is nothing more than the product of the yi's and the lambda i's, 1 to n, okay? Same notation for the x here, okay? So what this series is doing is it's recording the Smith partition in a way that records the composition, so I don't have a relation in there, as well as the composition related to the to a upper triangular matrix in that particular form. Okay? So, in order to understand this, sorry for going way back and forth here, to understand HSN, what we want to do is we want to map from the set of lattices. I'm not going to give it a name, I'm just going to describe the map. The set of lattices, we want to understand the fiber sizes of this map. So I just need to understand fiber sizes of this. Okay? And that's what we did in the Smith normal form case. That's exactly what this F is paid to do. I have a lattice, I associate with it a Smith partition, lambda. When I fix that, I fix a particular partition, this is recording a fiber size of, where's color? Of the map lambda goes to lambda lambda, if you'll allow me to say that. Okay? Now we're looking at an analog, we're looking at these fiber sizes here. Let's see how I'm doing on time. Excellent. Okay. A note for those that want to think about the generalizations, think about this thing a bit more general terms. Smith partitions, just say Smith, is intrinsic to a lattice. Right? It's the type of the abelian group of the quotient there. Forgot the p there. I do want to talk about p, even though it was fine what just said. Hermite is not. I've mentioned choices already. Okay? We don't need to choose a basis to get Hermite, though you could to get it. Instead, what we need is a flag, a particular flag. We need a flag. Okay? Well, let me tell you what kind of flag we need. It's called a complete isolated flag. Okay? So what do we have? We have that this is going to be something like this. Let me use the notation. Yeah, I'm going to just use the notation we have. So the U superscript i's, these are submodules, n-1, of zp to the n. So each of these are submodules, sub-zp modules, if you like, where each ui is free. It's a free zp module of rank I, and the consecutive quotients ui plus 1 mod ui is torsion free. Okay, it's torsion free. So there's a kind of simple example of this. You could take, of course, this is the 0, and you can take this to be a copy of ZP, say generated by a standard basis vector inside of ZP to the n. I'm going to use E1, for example. You have an E1, E2, so on and so forth, all the way up to E1, En minus 1, and then you get to your final, your destination. Okay, so that's something that's one example of a complete isolated flag when you have a basis already for that space there. Okay, so really what you need is this flag. It's not going to determine a normal form for you, but it is going to determine uniquely this. Relative to this flag, this is unique. Okay, and throughout the rest of my talks, I'm going to assume that I have a flag somewhere. Or I'm going to be working with matrices, or I've got, maybe a basis even. One of those. Okay, I don't want to mention much more because I only have 30 seconds. So, what we're going to do throughout the rest of the lectures tomorrow is we're going to look at this series, HSN. And actually, I think the tool to use to understand this are going to be Tableaux. These are the combinatorial objects to understand HS. Tableaux to understand. And we're going to prove that this is, understand the rational function. Check. I'll just write this simple relation here. We can use HS to get this particular subgroup zeta function. It isn't much of a surprise. We can do it in a few ways. One in particular is I can plug in all of the, for all of the variables x that are associated with the partition, I can plug in p to the minus is and 1s for the rest. So this is n variables, and this is the rest of the n. This is the y, and this is the x. And conveniently, you can see that here, the Agusa function. The Agusa function is somewhat related to, I kind of wrote it, erased it there, but it's related to the Smith normal forms. And that's where we see this coming in. That's that same minus is here, same reason that occurs. And of course, I can do this in the other way. I don't have to look at Smith normal form. I can instead look at Hermite, and this would be just p to the s n times. Okay, that's my y, that's my x. For now, I'm done. Thanks. In the torus, what do you mean by that? By Q mod Z? I don't know.
So isn't it the quadriatic dual of counting lattices?
Inside of Q?
Inside of Z to the n. Subgroups of Z.
Ah, yeah, that is the Pontryagin. That is the dual problem. That's the dual problem. That's right. That's the dual problem to counting sublattices of some fixed lattice, some Z lattice there. Yeah, by the Pontryagin dual.
So you have.
Yes, yeah, and so that does it. Yeah. I won't touch all the applications. So this is actually one particular application of something I'm going to introduce tomorrow, called the Hall-Littlewood-Schubert series. And that is what Christopher called the combinatorial Denef formula. That encodes tableaux, and that's our primary way of understanding this. That HLS series, the Hall-Littlewood-Schubert series, Seems to have a wide variety of applications, and in particular, certain kinds of series related to the symplectic group. I don't think I'll be able to get to it, all those kinds of applications in my mini course, but we can certainly talk about those. I think there's quite a bit of room to see some examples with this. Yeah. I could say something, actually. You could specialize this function if the Hecke series is a phrase that might make sense. The Hecke series associated to GSP, if you take a certain Fourier transform, i.e. applying a Satake isomorphism to get sort of polynomial variables rather than Hecke operators on that series, you can specialize this to that series, the Hecke series. It's a bit more complicated, but yeah, there are applications to this thing. More than I'm describing.